Good day. For this session, we'll talk about Thevenin's and Norton's theorems. We will compress an entire network into just two numbers. Whatever is inside the box, dozens of resistors, several sources, the load cannot tell the difference between the real circuit and a single source in series with a single resistor. That is Thevenin. Norton makes the same claim, written as a current source in parallel. The payoff is practical. Once you have the equivalent, you can swap the load 100 times and never touch the network again. You have all solved a ladder circuit with mesh analysis. And if one load resistor is changed, what will you do? Of course, you'll solve it again. You solve the same network a second time. Change it again, solve a third time. That is the waste we are removing today. Here is the claim. From the terminals, a linear network is indistinguishable from one source and one resistance. Thevenin writes it as a voltage source in series. Norton writes it as a current source in parallel. Same physics, two dielects. And notice, the resistance is identical in both. That is not a coincidence. We will come back to it. Two numbers, an open circuit voltage, and a resistance seen looking back into the terminals. That is all Thevenin is. 3 moves, always in this order. First, remove the load. And remove means open, not short. Whatever voltage appears across that gap is V open circuit. Second, kill the independent sources and look back into the terminals. That resistance is R Thevenin. Third, rebuild, source in series with resistance, hang the load back on, and solve what is now a single loop. Here is what matters. Steps 1 and 2 never mention the load. They are properties of the network alone. That is the entire economy of the method. Case 1 is the routine one. Suppress means, ideal voltage sources become short circuits, ideal current sources become open circuits. Then reduce by series and parallel. Case 2. No independent source means V open circuit is 0, so any ratio method collapses to 0 over 0. You have to excite the network yourself. Apply a test source, measure the response, and take the ratio. Case 3 is the trap. Do not suppress a dependent source. A dependent source is not an input, it is a constraint written by the rest of the circuit. Suppress it and you have destroyed the thing that defines the network. RTH equals VOC/ISC works in every case. Learn that ratio. It works with independent sources, with dependent sources, with both. If you are ever unsure, use it, suppress it, and you have destroyed the thing that defines the network. Here's a worked example. We have a 111 volt source with 6 resistors. R4, the 7 kilo ohm resistor, is the load. Everything to its left and right is the network. We are going to solve this twice. Not to fill time. Getting the same 5.25 milliamps from two completely different routes is the strongest evidence that the equivalence claim is real. Just take note, kiloohms with volts gives milliamps. Not amps. Milliamps. Open the R4 branch. No current flows there, which means IB runs cleanly around the right-hand mesh. Recall how mesh equations are written and write the mesh equations as you speak. Do not just read them. Mesh A, 111 equals 11 KIA minus 8 KIB. Mesh B, 0 equals minus 8 KIA plus 17 KIB. Press your calculators and solve. Answers will be 15.34 and 7.22 milliamps. Now walk KVL across the open gap and pick up V open circuit. 50.54 volts. Since no current enters the gap, IB simply flows through R5 and R6 in series. So V open circuit is just 7 kiloohms times 7.22 milliamps. Same answer, one line, no mesh walk. Two independent routes to the same number. That is how you check yourself under exam pressure, not by redoing the same calculation, but by taking a different path to it. Suppress means short the 111 volt source. Not remove it, short it. The wire stays. This distinction matters. A removed source leaves an open, a suppressed one leaves a wire. Now look into the gap from the terminals and reduce. Going left, R1 and R2 are now in parallel, because the short ties their far ends together. That gives 2.182 kiloohms. Add R3 in series, 4.182 kiloohms. Going right, R5 and R6 are simply in series. 7 kiloohms. Those two paths sit in parallel across the gap. 2.618 kiloohms. Why does R4's own 7 kiloohms never appear in this calculation? The answer is because it is the load, not part of the network. Now, let's reattach R4. There's only one loop. Just use Ohm's law. I4 equals 50.54 over 2.618K plus 7K equals 5.25 milliamperes. V4 equals 5.25 milliamperes times 7K equals 36.78 V. Now land the point that justifies the whole exercise. If I ask for R4 at 5 kiloohms, or 10, or a sweep from 1 to 20, you do not touch the network. You reuse 50.54 volts and 2.618 kiloohms. Every additional answer costs you 1 division. Now, let's have Norton's theorem. Everything you just learned about Thevenin, or RTH, transfers unchanged. Only the source changes form. Structurally identical, with one substitution. Where Thevenin opened the terminals, Norton shorts them. Where Thevenin got a voltage, Norton gets a current. Step 2 is literally the same calculation. R Norton, or Rn, equals R Thevenin, or RTH. Always. And step 3 swaps the voltage divider for a current divider. That is the whole difference. If you have done Thevenin, you have already done 2/3 of Norton. Let's have the previous problem. Watch mesh B carefully. This is the one thing that changes. With the short across R4, the right-hand loop no longer includes R5 and R6, the short bypasses them entirely. So mesh B's self-resistance drops from 17 kiloohms to 10. 8 plus 2. Mesh A, 111 equals 11 KIA minus 8 KIB. Mesh B, 0 equals minus 8 KIA plus 10 KIB was 17 K. Solve, I short circuit equals IB, 19.30 milliamps. And the resistance? We do not compute it. It is 2.618 kiloohms, exactly as before. This is where Norton pays for itself. Now, perform current divider, not voltage divider. The load takes the smaller share, because it is the larger resistance. I4 equals 19.30 M times 2.618 K over 2.618 K plus 7 K equals 5.25 milliamperes. V4 equals 36.78 V. 2 different equivalents. 2 different formulas. 1 physical answer. That is not a coincidence to be noted and moved past. That is the theorem being true, in front of you. This slide is the reason we solved it twice. Divide 50.54 volts by 2.618 kiloohms. You get 19.30 milliamps, the Norton current, without ever shorting anything. As you can see, VOC/RTH equals 50.54/2.618 K equals 19.30 milliamperes equals ISC. That is source transformation. It means the two theorems carry exactly the same information, encoded differently. Thevenin is not an exam artifact. It is output impedance. It is what tells you whether your sensor can drive your ADC. It is why an op-amp buffer exists. And it is the quantity that appears in maximum power transfer, when the load resistance equals Thevenin. You will meet this number again in electronics, and again in communications. Check out these common mistakes and how they can be resolved. To find V open circuit, do I open the terminals, or short them? To find I short circuit? Which sources am I allowed to suppress? Does the load go into Thevenin? If you remember one thing from this slide, the ratio V open circuit over I short circuit never fails. Independent, dependent, or both. Whatever is in the box, 6 resistors or 600, the load sees 2 numbers. Everything else is bookkeeping. Open the terminals for the voltage. Short them for the current. Suppress the sources for the resistance. Then reattach the load and divide. And Thevenin follows you forward. Output impedance in electronics. Source impedance in communications. The matching condition in maximum power transfer. Same number. Different course. Now, try this one. We have a circuit with 2 voltage sources. Apply the principles used in the previous example. This time, R3 is the load. 2 independent sources, none dependent, so RTH comes from straight suppression, short both voltage sources and reduce. The drawing is where the understanding lives. Find the current and voltage in R3 using A. Thevenin's method, and B. Norton's method. If you have questions, just message me. Keep it up.